So, my series of lectures is about measure equivalence of groups. So measure equivalence is a theory that allows you to realize some crazy dreams. For instance, you can pretend that every countable group contains a little order element. No notion. You can pretend that every group contains F2 as soon as it is non-amenable. As Foray mentioned, our result with Russ lines. If a group is non-amenable, then it measurably contains F2. And for some purposes, it's very useful. Some results were known to be true for groups containing F2, and they have been extended to all non-amenable groups using that trick. You can pretend that an amenable group is indeed a Z. Or, if you want, it is a locally finite group, a group whose finitely generated subgroups are finite. Okay, so according to the purpose, you can realize such crazy dreams. On the other hand, you have realized maybe that you have really two worlds. The amenable one, where the Ornstein-Weiss theorem and more generally the Cohn-Feldman-Weiss theorem implies that there is only one equivalence relation up to orbit equivalence as soon as they are ergodic. So this is the usual, you take your system, you let the group act, it preserve the measure, it is ergodic. Okay, there is only one partition of the space into orbits when you are amenable. While in the non-amenable world, well, many things have to be discovered, to be understood. But in the non-amenable world, we know indeed that every non-amenable group admits uncountably many non-orbit equivalent actions. Okay, this has been done by Greg Yurt in 2005 for Carleton groups, infinite Carleton groups. It has been done by Sorin Popa and myself the same year for 3 groups, F2, and then it has been extended to groups containing F2 by Adrian Johanna. I guess it's in 2011. And then in Epstein extended that from groups containing F2 to any non-amenable group using a trick with lines. Every non-amenable group contains F2 in a measurable sense. Okay, just understood me that many of you come or are very much interested in geometric group theory. So I guess that most of you know what quasi-isometric groups means. Okay? And the theory of measured equivalent or measured group theory arose with a paper of Gromov in 1993, where he gave a theorem and a definition. So the theorem is that 2 finitely generated groups are quasi-isometric if and only if they admit commuting actions on a single locally compact space, both actions being proper and co-compact. Okay? And then, so for instance, if you take let's say a Lie group, or more generally a locally compact compound group, and you let 2 co-compact lattices act, one by left multiplication and the other by right multiplication. Yes. Left, right. Okay? And these 2 actions commute and satisfy, so the lattice being co-compact, they satisfy and they are quasi-isometric. Now, what about more general lattices? This is the definition of Gromov. Instead of considering a topological coupling, you consider a measured coupling. So a space, a standard space with a measure, an infinite measure. So think in your favorite Lie group with its R measure, or more generally, a locally compact non-countable group admits the R measure. And you pick two lattices, and you let them act from the left and from the right. They both admit an action which is free, preserve the measure, and each action admits a fundamental domain of finite measure. And this is the definition of measure equivalent groups. Just you replace the group by, I said, standard space with a measure. The actions preserve the measure and have fundamental domain of finite measure. Okay? And this is maybe something you can check as an exercise. So if you have gamma 1 acting on the space omega n and gamma 2, so there's commuting actions. Of course, you can consider the action of gamma 1 on the quotient omega mod gamma 2. Here you have the induced measure, let's call it mu1. Okay, and you can also consider the action from the other side. So gamma 2 acting on gamma 1, omega of gamma 1 with the measure mu2. Okay, these two actions have some relationship, of course. Essentially, the space of orbits here and there is the same as the space of orbit of the action of gamma 1 times gamma 2 upstairs. So they have the same space of orbits. The notion is the stable orbit equivalence. So orbit equivalence is the standard notion that has been introduced before in the preceding talk. Stable means, well, essentially you see that you don't have the same measure, the co-volume. If the co-volume is equal, you have to adjust something. Okay? I will maybe come back today or tomorrow on that. Good. Anyway, you see that measure, so this is the notion of measure equivalence, and we write that gamma 1 is ME equivalent with gamma 2. And Gromov has this program of classifying countable groups up to quasi-isometry. And of course, the analogous program of classifying groups up to measure equivalent. Okay. By the Einstein-Weiss theorem, we very soon realized that there is almost nothing to do in the amenable world. We have two classes, the finite groups and the class of Z. Okay, they all are orbit equivalent with Z. They are measure equivalent. So in particular, orbit equivalent actions produce a measure equivalent. This can be left as an exercise, but you have this. Okay, no. Anyway, so measure equivalence is very much related to orbit equivalence, and invariants of orbit equivalence, or more precisely of stable orbit equivalence, become invariants of groups up to NE. Okay, and so the prototype, I repeat, here are non-co-compact lattices, or lattices that are not necessarily co-compact. Okay. So,
that's the question, actually. The so being measure equivalent, I mean, is it that there exists a space that they both act on?
Yes.
Like that, so that
Yes.
orbit spaces
So there exists a standard space with an infinite measure, usually measure. Okay. The actions are free and admit, each action admits a finite measure fundamental domain. This makes sense?
And also preserve the measure, right?
And also the preserve the measure, sure. The actions preserve the measure. So it was just an introduction. It was not meant to be a. Is it okay?
So any two lattices are measure equivalent?
Yes. In the same. Yes. Okay. So as I mentioned as I said, when they mentioned from Neumann and the relativity, the important notion is that of groups, and groups are made to act, of course. So the standard objects are now a group, countable group, acting on a standard probability space. And now the measure mu is invariant. So this is a PMP action. This is very nice because probability measure preserving, and in French, préservant la mesure de probability. It was in both languages. So PMP action gives rise to the associated orbit equivalence, which is a subset of x times x, the set of x, y, for which there is an element of the group sending one to the other. Okay, so this is equivalence relation that satisfies several properties. But one, the classes, yes.
Yeah, when you say when you actually talk about action, don't you mean that the measure is unimodular?
As soon if you have a lattice, the measure is automatically unimodular. Okay, because you know that it is unique. The R measure is unique up to the scaling, and if you have a finite portion, okay. So the classes are countable. Okay, 2 or alpha as a subset of x times x is a Borel subset, and 3 preserve the measure. And preserving the measure means, well, for instance, that for every partial isomorphisms, okay, so between A and B that are Borel subsets of X, so this is a bijection, a Borel bijection, it is automatically B Borel, okay? For every partial isomorphism, such that X and phi of X belong to R for every X in the domain A, then the measure of A and B must be the same. So as soon as the graph of your partial isomorphism is contained in the equivalence relation, then indeed it preserves the measure. That's clear? Okay, and now if you take this pre-definition, this pre-properties, you have the definition of a PMP equivalence relation. Okay? And you see, it is not very complicated. Usually, an equivalence, and you have this theorem of Feldman-Moore telling you that indeed every PMP equivalence relation is produced by an action, a PMP action of some countable group. That makes sense? Okay. So there is eventually no, well, this is there is no essential restriction in thinking of a PMP equivalence relation as being defined by a group action, right? And thus, the equivalence relation is just so a subset of x times x. So x, x, you have the diagonal inside the equivalence relation, of course, and it's just the union of the graphs of the phi i's of the elements of the group. This makes sense? And so, since the group is countable, you have countably many. Of course, I draw it continuously, just measurable. Okay, and thus you have the two projections, P1 and P2 on X. There's two projections of countable fibers. Okay, and thus you can define a measure mu tilde on R. If you, okay, now if you pick the subset C R, the measure of C see a Borel subset in x times x. What is mu tilde of x? Okay, so let's say it is you disintegrate the measure using pi p1. Okay, and you count how many elements of R you meet in the fiber of pi1, and then you integrate in x. So it's the number of elements in the fiber of x that meet C d mu of x. Okay, and here I put p1. This makes sense? So it's a measure on R itself. It is an infinite measure. But of course, I defined it using P1. I could have defined it using P2. Okay, and I leave as an exercise. Let's say mu tilde 1 equals mu tilde 2. This is exactly the same as saying that the equivalence relation preserves the measure. Okay, so you have a well-defined measure on R itself. Okay, which is defined using any of the two projections. This is in a sense the R measure of the equivalence relations. Okay, equivalence relations are examples of groupoids. Okay, and so it is R measure. Good.
Yeah, can I clarify? So basically, so P1 inverse of x can be infinite. We can have countable many.
Yeah.
You can, yes.
So
The measure is not finite.
but this is the
So it is a positive measure. You can integrate with the measure with the infinite.
I see. But what you're saying is an interesting example. Seeing the example we're interested in mu tilde is like it's like it's well defined on many steps. Yeah, like it's well defined. Basically, okay, what is mu tilde is that?
Excuse me?
What is like mu tilde of C is like everywhere? Okay.
It's a sigma finite method.
Oh,
It's a yes.
but if
Because you see, your measure of the diagonal is 1. And each
Oh,
graph I measure 1.
I see.
Okay.
Yeah.
Okay. So now you know the measure, the definition of orbit equivalence that's been given by Foray, I guess. Okay, and so for PMP equivalence relation or for group action. Okay, and it is really not clear. It's movie time, please. Did you foresee the popcorn? And so this small movie is just to show you an example of two groups that admit an orbit equivalent actions. Okay, it is not clear a priori that two non-isomorphic groups can have orbit equivalent actions. We know by on-spin bias that this is the case for amenable groups, infinite amenable groups. So here, the example is the example of odometer. So the odometer is a milometer, if you want. It's a dynamical system on string of sets. So you see you have the sequences of 0, 1, and it's an adding machine with carry digit. This makes sense? And of course, two sequences of 0, 1s are in the same orbit if and only if they agree outside a finite window. Okay, except for the exceptional orbit. I know this time when your car indicates 9999. And this exceptional orbit made only on one measure 0. For which measure, of course, we take the measure 1/2, infinitely many times. Okay, and so for this measure, the equivalence relation behind that is up to a set of measure 0. What is how did you call it? Eventually equality. Okay, this is the eventual equality. Okay, now let's consider an action of z squared. So you have a blue z and a red z. acting on two strings. So it acts on the product space. And now you can interleave the entries. So this is isomorphic to just one sequence of 0 and 1s. And again, 2 points are in the same orbit, if and only if they agree, the sequences agree, outside of finite range, up to a set of measures. So this shows an example of an action of z and an action of z squared that are orbit equivalent. This makes sense? Amazing, no? Probably it's amazing that movie. Okay, let's explore. So, yeah.
Are there questions in the chat?
I think this is from.
Oh, this is the
Okay.
okay. Maybe I stop sharing and close the. Okay. So now you know that this exists. A group action, different groups being with all equivalent action. Okay, and I can give you a proof that every action of an amenable group very quickly. So gamma, let's say amenable,
Sorry, what are you proving? Faking?
that this action is orbit equivalent with a z action. Okay. And so you have your space, you have the action of gamma, you pick one point in each orbit, you enumerate the group gamma. Okay, this is a countable group, you can enumerate the elements, the group, you pick one fundamental domain, the set that fits every orbit exactly once. Okay, and then you can identify the orbit of gamma with the orbit of z. Yes, just by sending gamma I of x to I. So you claim that you define the z action just that way. Of course, yes. It makes sense? Okay, this space fake for several reasons. One reason for which it is really fake is when I started saying pick the fundamental domain. This violates the first commandment. When the orbits are infinite, you shall not pick 1 point per orbit. Okay. When the classes are infinite, you shall not pick 1 point per x. Okay, and I will give you an exercise. So first of all, let's say there is a fundamental domain, domain D, if and only, so fundamental domain is D belonging to the measurable set. Okay, and such that for almost every point, all the orbits. So the complete section is it means that the measure of those x's such that the intersection of the class with the set Cn greater than 1. Usually this is infinite. Okay, when you have a complete section, so there exists such a sequence of complete section with measure tending to 0, but only if all the classes are infinite. Okay, and of course Cn belongs to Cn is a measure. This makes sense? Okay, good. So now you can prove using that that every Z action is equal to okay. Okay, so how is it? R is and more yes. R is hyperfinite if and only if R equals R alpha for some Z action. Okay, so I remind you that hyperfinite means that R is the increasing union of sub-equivalence relation with finite class. And what is hidden behind is the measure, or what is really very important is the measurability. Okay, the measurability condition, which is the point 2 here. Okay, you want the finite sub-equivalence relations to be measurable. This is why it is hard to achieve. And it was the same trick, first of all, when I picked a fundamental domain in general, this set was not measurable. It can be done using the axiom of choice, but it is not measurable. Okay, so I did this as an exercise. And now I define the graphing. So by a graphing, I mean the following: a collection of partial isomorphisms. Collection is supposed to be countable, a countable collection family of partial isomorphisms. Of course, it's a partial isomorphisms are Borel stuff, Borel objects, okay? And no, I cannot. Okay. So a graphing, I say, is a collection of partial isomorphisms, countable collection, and of course it generates an equivalence relation. If you have such a collection on all AIBI are subsets of X, and they are measurable, of course. So it generates an equivalence relation on X, let's say R5. It is the smallest equivalence relation such that X is equivalent with phi I of X for eigen I and X in the domain of phi I. Okay, this makes sense? And why is this called a graphing? Well, it's because it defines a structure of graphs on each class, on each orbit. Okay? So for each X in X, the class of X now becomes equipped with a graph structure. Okay? Let's say that a graphing generated equivalence relation R, of course, if R5 is isomorphic. Okay? And each graphing gives you a graph structure. How is it defined? Of course, the vertex set is just class of X, countable meaning points. Okay? And you have an edge between Y and phi I of Y. So it's an oriented edge from X to phi I of X, and it is labeled phi I. Okay? This makes sense? You have for each orbit a graph structure. And of course, since this is defined measurably, the graph structure is measurable. Okay? Another way of thinking of that is to say that on X, you have a huge graph. Okay? So the set of vertices is the wall of X, and you have edges between points in X. Okay? And this, you have certain measurability for the edges, and you want the connected components to intersect X on exactly classes. Defined classes, okay? So this is the notion of phi generates R if R phi equals R. And now for each graphing that is generating, you have a graph structure. Okay? So, good. As an exercise, you can, oh no, we do that a little later. Okay. No questions so far?
Are you saying that the phi's are measure preserving?
Yes. Sorry, I did not. Oh, measure preserving graph. You're right. I mean, if I want to generate R, which is PNP, then automatically the graphing are measure preserving. But okay. In general, if it is just Borel, I define a C there. Okay, good. Now you see, well, for example, so if you have a free PNP action of some gamma, and if gamma is a group that is generated by a finite set S, then of course each alpha of S is a partial isomorphism that is a complete full isomorphism, right? From X to X. And this collection defines you a graphing. It is a finite collection of Borel isomorphism. And I guess what is the structure of the graphs of the general graph on each class is isomorphic with the Cayley graph of the group with S. Okay? But now you see, since you have redundancy in between the generators of gamma, you have too much information in defining the equivalence relation using just the generators. And now it's movie time, please. As Forte explained, there is this example of rotations on the circle. So here, I consider two rotations, A and B, on the circle, and I assume that the angles are rationally independent, so that the angle of this square is free. I have a free action on the circle. Okay. Now, I can generate the equivalence relation by using the graphing phi made of A and B. But I claim that I can also generate it by using A defined everywhere, but B defined only on a small interval of the circle. Okay? So here the picture shows the angle of rotation for the blue one, for the red one. It's not important, the exact values. It's not clear. The colors are not that neat. Okay, anyway, now, so we have here A and B defined everywhere, and now we will decrease the domain of B, right? So here I have one point, X, a typical point, and the phi of X is isomorphic to the Cayley graph of this square. And now let's decrease B. It means that we remove some blue edges here and there. Okay? But look, it remains connected. So it generates the same equivalence relation. Okay? And the point is just that the red one acts ergodically. So you can, if you erase some blue vertical edge, okay, some problem, you can go very far away, you will meet the domain, and then be able to jump to the next level. That's clear? Okay. And so this is the notion of cost. You can generate this equivalence relation using A defined everywhere, cost 1, plus B defined on a small piece. Yes.
No, I just wanted to clarify, sorry for not stupid question, just for definition of B. So when we decrease the interval, what you say, okay, we might make the, like a single jump, we might not hit the interval, but if we do the too many times, we hit the, like, how do we define the restriction of B? Or small interval?
So B is a rotation. Now I restrict its domain to this small interval, and I let this small interval move from this angle to that interval.
Is it the first return map?
Excuse me? No, it's not the first.
Oh, I thought.
It's a partial isomorphism
Ah,
defined as B restricted to a small part of its domain. Yes?
The B here is like a different A there. The little blue interval is like A.
Ah, yes, that's true. So it should be AB. And subscript B. Oh, yes. This is, I'm sorry.
I think that's why.
I see the problem. Sorry. Okay. What else? No, that's all. But now, if you move the point X, so I have picked some intervals where A and B are defined, the rotations, and I move the point X, and you see the various graphs you obtain with this graphing and the parallel universe seen by the different points X. Okay, and here it's when the domains are too small. You see? Here the connected components are finite. This graphing does not generate the equivalence relation. Okay? Good. So now it's time to define.
I think some of us are still confused. Would it be possible to explain it again?
So like in the like Haley graph you're drawing, an edge exists there if like after you translate these two sets by like A, B, they're overlapping. Is that what's like what draws the edge between them?
An edge exists if the corresponding point of the orbit belongs to the domain of the rotation. Okay? So since the rotation A is defined everywhere, you have all the horizontal lines, but the vertical lines only exist when you are in the point of the orbit of X that belongs to the domain.
In other words, keep all the edges as in the beginning, Z squared, yeah? Then erase all the edges, whose like, left endpoint is not in his domain. So only keep those edges whose left endpoint is in the domain.
And then as you move up, you translate the set, or you like rotate the set.
We were not moving up, like in the fixed domain B, like they just fix the small set B, and I'm saying erase all the edges that don't touch that set.
Okay.
Every test of X to be exactly the image of the movement. I do. You fix just the domain and then you let the codomain be exactly the median.
Maybe a different construction is that you do the other way around. You start with your red edges, so you have your lines, and then you observe like what happens with the blue ones. So like now you have like your circle is like dividing those red lines, and now you look at like you start from your small blue thing and you look where it moves, and this is going to give you the blue edges. The blue edges. Yes. Okay. Yeah, that makes sense.
Okay. So now, if you have a graphing that generates an equivalent relation, if for phi, the graphing, the cost of phi is defined by, well, essentially the number of elements you have in phi, the number of partial isomorphisms, weighted by the measure of their domain. Okay, so it is just the sum of the measures of the x, which is of course the sum of the measures of the giants, which is of course 1/2 the sum of the measures. And this trick can be useful for an exercise in class. Okay? Oh no, I can't do it right now. Using that, show that this quantity is exactly 1/2 of the mean valency of the graph phi of x. Okay, so you have for each point x in the space the x, you can look at the valency of the point in its own graph. This makes sense. Okay, and so this is the mean valency, which is the cost of the graphing. Now the cost of the equivalence relation R is just the infimum of the cost of the phi such that phi generates R to a set of measures here. And so in the example of the square action, the cost was 1. Okay, so 1 plus epsilon for every approximation, and the infimum is 1. Indeed, since we know the Einstein-Weiss theorem, we know that the z-square action, indeed this was proved already for the square by that. Okay, so we know that indeed this action can be produced by an action of z. Okay, which means that you can equip each class with a lining, or with the structure of a line. Okay, cost 1, and which means, well, when the orbits are infinite, the cost must be greater than or equal to 1. Okay, so if you have a line structure on each orbit, the cost is 1. That's clear? Okay, now what is the cost of the group? Gamma is the infimum of the cost of R alpha for every over all 3 PMP actions. Okay, so you pick your group, gamma, you look at all its reactions, you compute the cost for everyone, and you take the infimum. Okay, so this is the inf cost, and of course you have also the supplement cost, which is the same thing with the sub. Let me mention right away that in all the examples where it has been computed, there's 2 quantities agree. Okay, so the group is said to have fixed price if the infimum cost equals the supplement cost. All the 3 PMP actions have the same cost. Okay, so this is the cost is really the analog in the measured group theory to the number of generators, the rank for a group. Okay, you can see as an exercise also that here the cost of an equivalence relation R is the infimum of the graphings in this sense. This is also the infimum of the measure mu tilde of C. I remember you, mu tilde is the measure on R itself, such that C is contained in R and C generates R. Okay, a subset of the group generates it if applying the group operation you generate, you have the whole group. A subset of an equivalence relation generates it if applying the transitivity, the symmetries, you get the whole equivalence relation. Okay, good. So sorry, there is an inf missing here. Okay, and so let's say this is an exercise. This equality. Okay, good. So let me fixed price. Gamma as fixed price means that the infimum cost equals the supplement cost of gamma. So all known, when it has been possible to compute, we have no examples. This is the first open problem. Does there exist non-fixed price? Fixed price groups.
An exercise for the power trade.
Yeah. Okay.
the top equality on the right hand side, some of these measures to be equal to the average degree. You need to assume something like if you have one isometry that takes a vertex somewhere, there's only one.
Are you trying to solve the exercise?
No, I just, you need to like assume something about these graphings, like there aren't parallel edges.
Consider them.
But then you do it. Then you do the same, then the upper, the superior costs.
What I can say is that both are known to be realized, but this is realized by abstract nonsense.
But it's a supremum of the thing.
Sorry?
It's a supremum of
Of the whole action, all three PNP actions. So this is known to be realized by the Bernoulli shifts. This is a result of Ornstein pipe. Sorry, and this is known to be realized also by abstract nonsense. You take a sequence that approach the infimum and you take the direct product of this action. This produces an action with the infimum cost. Okay, and now the main, essentially the first, the foundational result for cost. So I should mention that this definition of cost for graphings and equivalence relation is due to Levitt, Gilbert Levitt, in 95. And it was unknown whether the cost could be a non-trivial invariant. Okay. It could have been, since we have many examples of the cost equal to 1, it could have been that the cost of a group well, be always 1. It did not. This is not the case. And so this is this theorem I put in 2000. Please realize the costs. So of course, once we have graphings, you can guess what a tree is. Each graph is a tree. It has no loops. Okay? And so more precisely, if psi is a treeing of R, then the cost of R equals the cost of that particular graphing. Okay? For instance, when you have a free group, free on n generator, you know that n is the minimal number of generators for that free group. The same holds here. So it's quite easy to show, and this is an exercise, that in case the cost is finite, so you have a graphing that satisfies this equality, and it is finite, then it must be a tree. Of course, if you have cycles, then somewhere you can remove edges and still have connected graphs. Okay, so this is an exercise. Prove the converse, I mean that it is a treeing when the cost is finite and realized by some graphing. Okay, and so as a corollary, we can say that the cost of the free group on n generators equals n, and it has fixed price. That's why I don't need to start it. Of course, if you take a free axle of Fn, which is PNP, then you take a free generating system and you consider the graphing associated with the generators, the free generators. This gives a structure which is the Kerr graph of a tree. So you get a tree. Okay, and this implies that instance F2 and F3 have no orbit equivalent actions. Okay, because of course the cost of an equivalence relation, it is invariant under orbit equivalence. Okay, and this is the number must be 2 in one case and 3 in the other one.
Yes, is this true when n is infinite?
Yes. The cost is infinite.
Yeah, okay. Yeah, okay, right. No, it is.
The cost of SL2Z equals 1 plus 1 over 12. Okay? You know that SL2Z is very close to be a free group. And indeed, SL2Z decomposes as a free product with amalgamation of Z over 6Z with Z over 4Z over Z over 2Z. Okay? So it's A, B, C with A, B, C finite. Okay, and this is a more general result. In this situation, if you have a free product with amalgamation of finite groups over a finite group, then the cost, then this is treeable. You can equip the orbits with free structures, okay, and then you get 1 plus 1 over C, the cardinality, minus 1 over A, minus 1 over B. Okay. Maybe write it here. The cost of such a group in general is 1 plus 1 over the kernel of C minus 1 over A. Good. So, for instance, so a group is said to be treeable if it admits a treeable action, so an action which is free and that admits a tree. Okay. So these groups. So for instance, it is good, but surface groups. Why? Well, you know, a surface group, let's say a hyperbolic surface, is a lattice in SL2R, the same as the free group F2. And so by letting them act on the right, on the left, you have SOE action, but is very, very close to OE action. And so you transfer the treeability from. So surface groups admit one action that is treeable. Okay? Indeed, we know since quite a small number of years that it is the case for all the 3 PMP actions of surface. This is the result of Clinton, Colway, Andrew Marks, and Robin Tucker. Okay, these groups have ergodic dimension 1. Okay, you can equip their free action with the structure of a graph, which is without loops. So the structure of a, let's say, simple complex, which is one-dimensional and contractible. Dimension 1. You know, there is a notion of dimension for groups, geometric dimension. What is the smallest dimension of a contractible space on which your group acts freely? Contractible, let's say, a contractible simple complex or CW complex on which your group acts freely in a CW compatible way. The complex being contractible. Okay, this is the dimension of it, geometric dimension. You have the analogous here, and I will try to explain you that in the next, in my next lecture. Just, of course, I just said half of what I wanted to say, but we have another corollary of this. You know, it is that if you have an action that admits a tree, if you have a group, sorry, group gamma, if gamma admits tunable free action, free PMP action, alpha 0, then alpha 0 realizes the infimum. It's just, I told you that it is realized, this cost, by taking direct products in among the actions we consider in the direct product, you can insert alpha 0 itself. So you have an action that factors onto alpha 0. And there on alpha 0, you have a tree, and you can pull back it. So you have a tree upstairs. Okay, and so this is a tree, this is a treeable, equivalence relation, and it's realized in infinite. Okay, so and when you pull back, you have the same cost. Okay, so and this implies that if gamma, let's say, is non-amenable and as cost equal 1, then it is non-trueable. It admits no trueable free PMPI. Its ergodic dimension is greater than 2. Okay?
I guess, yeah, I mean, it was implicit, but we should say, yeah, amenable groups have cost 1.
Yes, exactly. This is an example. I ended it in the sense that infinite amenable groups have cost 1. They are fixed price. They are trueable. Indeed, they are lineable. Okay, because their free PMP actions are orbit equivalent with a Z free action. Okay, so we can transfer the line structure. Okay, and well, for instance, the cost of a group that decomposes as an amalgamated free product over an amenable group, let's say amenable infinite, then the cost is the sum of the costs minus 1. Okay, cost of this, cost of that, minus the cost of this infinite amenable. Okay, so for instance, surface groups have costs 2G minus 2 if G is the genus for an orientable surface. Okay, so maybe you're hungry. It's time to stop. Okay.
Maybe a couple of angry folks.
Is it easy to write down the cost if you have a more general graph of groups?
No, it's not that. It's not easy in general. Okay, we have many examples of groups. So you understood that when you have this square, you have one generator. Okay, and now you can pick a very small domain using an exercise I left you. A very small domain that meets every phi1 orbits, say. And then you can jump and define phi2 on this small domain. And you can continue this. So if you have a group, which is the so-called chain commuting, generated by a chain commuting family, so elements of infinite order, so that the first one commutes to second with third with, and so on. This has cost 1. So for instance, you see SL3Z or SLNZ and greater than 3, SLNZ is generated by matrices, with 1s everywhere, 0 elsewhere, except in one case where you have an exceptional one, in case I, J, right? Now, so this is a matrix, let's see, A, I, J, A, I, J commutes with A, K, L, as soon as G is different from K, and I different from L. Okay, and these elements that generate SLN of Z when L is greater than. Okay, and with these arguments, we can show that it has cost 1.
My question was different. Like if you have an HNN extension.
Sorry?
If you had an HNN extension?
HNN extension. Okay, sorry. So for an HNN extension, you have the same result. Yeah, the same type of result, HNN extension above an amenable group.
Yeah.
Yes, same type of result. But this is a very important family of examples. And indeed, this shows that other lattices in SLN have admit one action of cost 1. And some of them are known to have fixed price by my ancient, so non-co-compact lattices and okay, but and recently some with 2 co-authors announced secret. It's not available so far, that lattices in higher rank Lie groups do have fixed price. And this is a very important result in the theory, except especially because it is related, for instance, to the rank gradient. You know, when you have a finite index subgroups, how many generators do you need to generate these subgroups, and how does this sequence of ranks grow when you go farther and farther into finite index subgroups. If you take finite index subgroups of higher and higher index, okay, and this should converge to 0 for all lattices according to your result. So it's with Nikolai-Franchik and Willems, right? Amanda Wilken. So
Other questions?
So,
Hold on.
in the last meeting, there was like those intervals that didn't quite span the whole, is the definition of the intervals? No, it's just like the
it's quite an arithmetical stuff.
Okay.
We can discuss this because this relies on the former work of Levitt, and that led him to introduce the notion of cost. And he was interested in transversally measurable, transversally measured foliations on manifolds. Co-dimension one manifold foliation are transversally measured. And in order to understand that, you have to make the same the kind of stuff. It's a very complicated and very nice picture. You have Sierpinski basket appearing in this one. It's okay.
Okay, any more questions?
There is an online question just here. So is the fixed price property preserved when passing to the finite index subgroup?
There's also like this.
Yeah, no, it works only in one sense, in one direction. If the ambient group has a fixed price, then the smaller the finite index subgroup has fixed price, but not the context. I know. I mean, it is not true for the context, and this is part of the difficulty in this rank gradient stuff.
Okay, no other questions? Again.